Greetings! Today a demonstration of the all-important Le Chatelier's principle in chemistry, one of our most important ideas that relates to chemical systems in this concept of equilibrium, where both the forward and reverse reactions can happen, and as a result, conditions dictate that those rates become equal, and we have the so-called condition of equilibrium. It's hard to show you this equilibrium system because we kind of need something that has color, and the color then can substitute for changes in that equilibrium. And so our most, common demonstration involves the formation of complex ions, which are the vividly colored ions in nature. We don't say anything really about them in Chemistry 121. Here then the equilibrium chemical reaction between iron 3 nitrate and potassium thiocyanate to produce aqueous solutions of potassium nitrate and this complex ion here, iron thiocyanate. Oftentimes we simplify these reactions to get rid of the species that aren't doing anything. We call those spectator ions. And I've done so here to highlight the playas, as they say, the iron 3 ion in solution, the thiocyanate ion in solution, and this complex ion, iron thiocyanate, with a charge. And that's what we're going to be monitoring. The bottom line here is that the iron 3 ion in solution is sort of a pale orange. The thiocyanate ion in solution is essentially colorless, but when we mix them together, we get this beautiful blood red solution of iron thiocyanate. And so the difference in color here allows us to pretty easily test Le Chatelier's principle by introducing disturbances to the equilibrium. The iron 3 thiocyanate and iron thiocyanate ions are in equilibrium in this solution. As you watch it, the iron ions are bumping into the thiocyanate ions and making the iron thiocyanate complex ion. At the same time, the iron thiocyanate ions are bumping into each other and remaking the ingredients. And the consistent color indicates the position of that equilibrium. But the bottom line here is anything that we do to shift this equilibrium right should produce a darkening of our solution. And anything we do to shift this equilibrium to the left should produce a lightening of solution. I will leave this test tube alone, and that will serve as our control. And I'm going to take these other test tubes and experiment with them. The first thing I'm going to do is get my reagents.
So we were all ready today, and then we were doing all of these at once, and so it looks like he might have left the reagents back in the stockroom. But look, he's back.
I'm back. And what we're going to do is we're going to add some iron 3 ion to our equilibrium. Here we go. Just going to take and add a little bit to one of these 3 test tubes. And the question is, does the solution get lighter or darker or stay the same? Well, here is the one I added the iron to. Here is our original solution. What do you think? Hopefully you can all see that the solution got darker. And indeed, this makes perfect sense from the perspective of Le Chatelier's principle. Adding a reactant pushes the position of equilibrium towards the product, and the solution got darker as a result. The shift then in color suggestive of what happened to the equilibrium. It's very difficult to remove ions from solution directly, and so what we have to do is resort to kind of a chemistry parlor trick. In this case, I'm going to introduce some silver ions that are going to scavenge some of the thiocyanate ions out of the equilibrium solution. Here then our original Here our test solution. Two things have happened. One is the solution has definitely gotten lighter. And also, if you look very, very carefully, you can see the cloudiness. That's the result of the precipitation of some solid silver thiocyanate. Consistent, again, with Le Chatelier's principle, which holds that the removal of reactant, in this case by sequestering it as a solid, causes the equilibrium to shift back towards the reactants, which again in our case means the solution gets lighter as the abundance of the iron thiocyanate complex ion decreased as a result of the removal of the thiocyanate ions via a side reaction. So again, consistent with Le Chatelier's principle. Finally, the really exciting part to me is the linking of our Le Chatelier's principle and equilibrium to thermodynamic considerations. And so the question I posed for you here, and this is a hard one, is this reaction forward exothermic or forward endothermic? That is to say, is heat a reactant or a product? And the beauty here is that we can actually test this by taking our equilibrium system and adding heat to it. And over there on the right, you see a test tube that I put in a beaker of hot water a while ago. Here is our original solution, and here is our heated solution. Hopefully everyone can see that the heated solution is lighter than the original. And if we follow Le Chatelier's principle, we can see that because the addition of heat caused the equilibrium to shift toward the reactants, that heat must be a product, because when we added it, it shifted away. And if heat is a product, we can conclude that the reaction as written is forward exothermic.